It's time for our first actual talk of the day, which is by a very frequent speaker who I didn't have to look up the introduction of, because every time I look at his talk, it's like, wow, I learned something very deep about Go. So, small applause for Jesus.
Hello, everybody. Well, I'm going to talk about the secret life of a goroutine. This comes from my interest about how Go works internally, and I was investigating how the goroutines works internally. So when I start investigating it, my idea of how goroutines were created and all that stuff was something like this. A caring mother with a baby in her arms, taking care of that beautiful, full of joy baby. It wasn't like that, okay? I started digging into the code and I realized that it's more like this, a necromancer raising the dead. And I'm going to explain why, and there's a reason for that. But before that, I'm going to talk about something more general, that is the Go scheduler. For understanding how the goroutine works, we need to understand how the scheduler works and how it is shaped. So, let's start with the different pieces of the Go scheduler. One of them is the P extract, that is the representation of a virtual CPU. Whenever you say Go max procs, what you are saying is the number of Ps that the scheduler have. And a processor, as I said, is a virtual representation of the CPU, can have a status that can be either running, syscall, or gcstop. It has associated the current M. We are going to see what an M is in a moment. Then it has, each processor has a queue of goroutines that needs to be executed and a list of free goroutines. We are going to see what free goroutines are later. And, of course, other metadata. This is a very shallow explanation of the scheduler. This is an oversimplification. Of course, it's more complex than that. But, well, a lot of other metadata inside the P extract. Let's talk about the M. The M is it's a representation of an operating system thread. It's what is executing your code in the CPU. And it has associated normally the current goroutine that is running in this M, in this machine, and the current processor that is associated to this M. That can be null, actually. There's some cases where the M is not associated to a processor. But in general, they are associated, and other metadata. Let's talk about the scheduler itself. On top of all these M's and P's, there's a struct that is called sched. That is, it has a list of all the idle M's, all the M's that are not doing any work, all the idle P's, processors that are not doing any work, all a list of global runnable goroutines, a queue of work that is not associated to any specific processor for now, and a list of global free goroutines. Okay, and the star of our show, the goroutine. There's a struct that is called gstruct. That struct represents a goroutine, and a goroutine is composed by in a lot of stuff, but mainly you have a stack that is 2 kilobytes chunk of memory, the program counter that is similar to the program counter in a thread that is pointing to the next, to the current instruction that is executing. The status of the goroutine that can be running, waiting, runnable. There's a lot of different statuses. The current M that is associated to this goroutine is being executed right now. And the wait reason. The wait reason is if the goroutine is waiting, they have to be waiting for something. There have to be a reason for waiting. And that's the wait reason. There's a lot of other metadata. But let's take a look at the whole picture. As I said, we have the scheduler at the top left with a list of free goroutines, a list of runnable goroutines, a list of idle processors, idle machines. And we have running processors with running goroutines associated with machines and all that stuff. Also, another interesting thing is that at global level in the runtime, as global variables, we have a list of all the amps, a list of all the Ps, and a list of all the goroutines. That three lists are three global variables in the runtime. Okay, but how goroutines are created? This is where the necromancer raising the dead metaphor comes into place. Because whenever you create a goroutine, what you expect is you spawn a new goroutine and start running things on that. But that's not what is happening. There's two ways of creating a goroutine. One option is to create it from scratch, and the other option is to reuse an old goroutine that is no longer working. So this is what is happening. Whenever a goroutine finishes, it's changed the state to dead. Okay? So all that free goroutines, actually they are dead goroutines. So whenever you need a new goroutine, you can reuse one of them. Or the other option, if there's no free goroutine or dead goroutine to reuse, you create a new goroutine full of life, you kill it, and then you raise that from the dead. So that's the process, and actually that is how it works in the source code. Was kind of shocking for me, and was a funny way of representing this. So let's see an example of that. Imagine that I have this goroutine here that wants to create a new goroutine. What it's going to do is pick one of the free goroutines in the free list and raise that from the dead, convert that into runnable, put that in the queue of the runnable goroutines of the processor, and call the scheduler, and the scheduler is going to eventually execute that goroutine. Another option is this goroutine here wants to run a new goroutine, spawn a new goroutine, but there's nothing in the free list of the processor. So it's going to go to the global free list of the scheduler and pick a chunk of them, move them to the processor, and then pick one of them and raise that from the dead and add it to the queue. And finally, you have the option of this one wants to create a new goroutine, but there's nothing in the global queue. So what it's going to do is create a new goroutine, it's going to kill it, and then it's going to raise that from the dead and put in the queue and all that stuff. So that's how goroutines are created. Let's see how goroutines, how is the life of a goroutine. A goroutine can go through a lot of different states, can go to runnable to running, from running to waiting, from waiting to runnable, from running to preempted, from preempted to waiting. There's a lot of stuff. Let's see all these transitions one by one. From runnable to running. That happens when you, for example, have a goroutine have finished the job, or a goroutine start waiting for something, so it's going to call the scheduler. So the scheduler is going to try to find another goroutine to execute. The first thing that it's going to do is try to find a goroutine in the local processor, in the runnable list of the local processor. If there's nothing, it's going to go to the global runnable queue, and it's going to take some of that, it's going to move that work into the processor, it's going to schedule one of that goroutines to be executed. Then if there's nothing in the global queue, it's going to go to the net pool. The net pool is this system that allows Go to do I/O work in an efficient way. And what it does is do the I/O work, and whenever it finishes, it gets the goroutine runnable again. But sometimes what we do is we need to find work to do. So we go to the net pool and check if something is already done and start executing that. If there's nothing in the net pool, we are going to still work from other processors. And if not, we are going to help the garbage collector in the mark assist phase. Well, in the mark phase. Well, once we have found a goroutine in all that process, We are going to mark that as running, and we are going to assign the machine, the operating system thread, to that goroutine. We are going to mark that as running, and we are going to start executing the code. Another option is running, another change is running to waiting. One of the interesting part of this is it exemplifies how goroutines are cooperative entities. So they cooperate to give you the sensation of concurrency. So the goroutine, when the goroutine needs to wait for something, it's the own goroutine who parks itself. Whenever I have to write to a channel, for example, if the channel is not buffered and I have to wait for something, what I'm going to do as a goroutine is park myself, stop myself, change my state to waiting, set the wait reason, detach myself from the operating system thread, and run the scheduler. It's the goroutine that is marking itself as waiting, the one that is calling the scheduler to schedule the new goroutine. So, and the scheduler is going to find another task and it's going to start running that. So, what are the reasons why we can wait? If you go to the Go source code, and actually there's in the bottom right corner, I usually put some references to the Go source code. But well, if you go to that point in the Go source code, you are going to see the wait reasons. And that's the list of all the wait reasons. There's no more, there's no less. That's all the wait reasons. Don't pay too much attention to that. I'm going to summarize that. If you want to take a look, you can go. But the summary is you have GC reasons, garbage collector reasons, mutex reasons, semaphore reasons, channel reasons, sleep reasons, and IO reasons. That's mainly why the goroutines waits for something. Okay, from running to syscall and to running or runnable again. Well, the syscall is an interesting part. The syscall is basically calling the operating system to do something, and that can be fast or can be slow. And for some syscall, it's kind of obvious, but for some syscall, it's not so obvious. So what it does is, whenever you enter in a syscall, whenever you try to execute a syscall, it's going to detach from the processor, and it's going to detect if the syscall is slow or fast. And if it's a fast syscall, it's going to finish the syscall and go back directly to running. But if the syscall is slow, it's going to just stay in syscall state, and it's going to detach it's going to keep the processor detached, so the processor can select another goroutine to execute, and it's going to finish the syscall eventually, and whenever it finishes, it's going to move the goroutine to runnable again, and enqueue that in a processor and all that stuff. The other thing that is interesting is the copy stack status. Whenever a goroutine needs to grow the stack, because it needs more space for the function parameters or for the local variables of the function execution, it's passed through this process that it's going to move from running to copy stack. It's going to reserve the double of the current stack size in memory, copy over all the information from one place to another, and change the pointers, and then it's going to move back from copy stack to running again. From waiting to runnable, this is a very interesting case because, again, as I said, goroutines are cooperative. So normally, when a goroutine is changed from waiting to runnable, whenever other goroutine calls go ready. Whenever all the other goroutines say to my goroutine that is ready to keep executing. We are going to see examples of that later. So whenever go ready is called, for example, if a goroutine is sending something to a channel and some other goroutine is waiting, it's going to wake up that goroutine. It's going to mark as ready, that goroutine. Then it's going to mark as ready. It's going to add that to the queue of the processor and try to get a processor to execute that. Another way is when you reactivate a list of goroutines. That happens, for example, when the garbage collector have to reactivate some of the goroutines that were marked as waiting for the garbage collection phase, for the mark phase. And when that's finished, it's going to wake up a list of goroutines. Another case, it's when there's a case where it doesn't need to wait. Imagine that you say, hey, I'm going to wait for X, but that X is already fulfilled, so I'm going to go back to runnable directly. And another thing is when you are trying to find a goroutine to execute, the scheduler is trying to find a goroutine to execute, you check the scheduler, you check the net pool, and the net pool sometimes have these goroutines that in theory they are waiting, but the data is already there or the job is already done. So it just move that up from waiting to runnable. Okay, from running to preempt, to waiting or runnable. Okay, Go, it's a preemptive, has a preemptive garbage collector, or has a preemptive runtime. And what it does is when a goroutine is executing for too much time, the system monitor is going to detect that and is going to send a signal to the operating system thread that is executing that goroutine. That signal is going to mark the goroutine as preempt, so it's going to be moved from running to preempt, and eventually the goroutine itself is going to find the time for moving from preempt to waiting, and after the next garbage collector scan, it's going to move from waiting to runnable again. So again, this is the whole life cycle: runnable, running, syscall, waiting, preempt, copy stack. Now all these states should be more obvious or more clear to everybody. There's also some other kind of similar states or parallel states related to the garbage collector. This is again a bit of a simplification, but this is in general what is the kind of states that you have in the goroutines. So let's see some examples. Imagine that you have a channel and you want to send data to that channel. The channel is not buffered, and there's nobody else waiting for that. So I try to send the data, and because nobody's waiting, I'm going to need to wait for that. So I'm going to park myself, the goroutine is going to park itself, it's going to add itself to a list of goroutines that is inside the struct of the channel, and it's going to wait there. So it's there, it's waiting, and eventually another goroutine comes to read from that channel. What it's going to do is go there, read the data directly from the memory of the other goroutine, and then when it has the data, it's going to call go ready on that goroutine, saying this goroutine is already prepared to keep going. It's going to, and that's going to end in this state, and eventually the scheduler is going to select that goroutine to be run, and everything is going to keep going. Yeah, this is the whole picture, trying to send the data, waiting inside the channel, getting the data from the other side, and the other goroutine is the one that is responsible of waking up the goroutine that was waiting in the channel. Let's see another example. Let's talk about the wait groups. For example, I can create a wait group and add 3 in this case. This is a very common pattern. And then I spawn 3 goroutines that are going to do certain work in parallel. Then I'm going to wait. At that point, maybe one goroutine is already running, maybe not, doesn't matter. So I call wait, so I'm now waiting. The goroutines keep going, maybe some of them are executed, maybe some of them have finished already, doesn't matter. Some of them finish and are dead. And the last one is going to call done, the last done, and it's going to see that, hey, the weight group is already 0, so I'm going to call ready on the list of goroutines that are waiting for this weight group. So that ends up with this situation where that's a runnable goroutine that is going to eventually be executed by the, it's going to be scheduled by the scheduler, and that's it. Again, the whole picture here. Okay, let's talk about how goroutines die. There's a goroutine normally dies when it finishes the work. Basically, whenever there's nothing else to execute, it's going to change the state to dead. It's going to set most of the data to the 0 value. It's going to disconnect the goroutine from the M, add the goroutine to the free list of the processor, the dead goroutine to the free list of the processor, and call the scheduler to find anything else to execute. So, yeah, the whole life of the goroutine. Again, if you see, this is the scenario where the goroutines are doing things. If I did my job correctly, you now should understand this better. And also, this should sound familiar too. So, let me finish with a couple things. One of them is I want to thank Laura Pareja, the one that did all the illustrations for this talk. All the illustrations are Creative Commons by, and you can see the webpage of Laura Pareja. So you can reuse it, do whatever you want with all that images. Also, I have a gift from Mattermost, that is my company, the company that I work for. I have some stickers. I'm going to leave that stickers there, like Margit said. So that's exactly right there. So feel free to pick as many as you want. But yeah, I don't know if, I have some pins too. So, but they are going to fly probably. So. Another thing is what is missing. I haven't talked about certain things because in the sake of simplicity, I try to avoid getting too much into the details. One of the things that I remove from the equation and have a lot to do with goroutines is garbage collector. I ignore the garbage collector entirely, and it's a big chunk of how the scheduler interacts and how the goroutines are moving from one state to another and all that stuff. The net pool, I mentioned the net pool, but I haven't entered into the details. There's very good talks about the garbage collector and the net pool out there. I ignore SIGO. Also, SIGO have certain implications with the goroutines also, but I have ignored them. The mark assist phase, that is kind of important, or it's a relevant part of things that goroutine does, as assisting the garbage collector in the mark phase. And the system monitor that I have mentioned, but I haven't talked in detail about that. But again, there's talks around system monitor out there. Some references. One of the main references is the Go source code. I totally recommend you to go there and explore it. There's illustrated tales of Go runtime scheduler that is a YouTube video there, and there's a series of posts from Arnold Labs about the Go scheduler. It's from 2018, so it's not super up to date, but the general patterns are still there. Well, I hope this talk, after this talk, you'll have a better understanding of how the goroutines work, how the goroutines change from one state to another, and all that stuff. But I want, what is more important to me, I want to encourage you to go there and explore the Go source code, because it's a great source of information. There's a lot of super cool stuff there. And depending on a combination of your passion about learning and your taste about movies, this can be more exciting than a zombie movie. So thank you. Okay. If you want to keep in touch with me, feel free to contact me. And the other thing, if you want to have a follow-up session I'm trying this. If you want to have a follow-up session, asking questions or whatever, feel free to join there.
If you're leaving